Hey there, statisticians. Mrs. Crum here from Skew the Script. Today we're going to talk about unlikely heroes and do some calculations using normal curves. Let's skew it! Today's lesson is on normal curve calculations. Let's jump in. This is Jose Fernandez, a former Major League Baseball pitcher. Fernandez was originally from Cuba. In interviews, he described growing up in poverty in Cuba, often playing baseball with sticks and rocks as a child, because he couldn't afford official equipment. When he was a young adult, after 3 failed attempts, he was able to successfully defect from Cuba, traveling by boat to the United States. And on that last journey, he famously saved his own mother from drowning in rough seas. With Fernandez and his family risking so much to come to the United States, once he arrived, he worked incredibly hard and became a highly successful baseball player. He worked his way up and eventually became the best pitcher on the Miami Marlins Major League Baseball team. He was known throughout the league for his cheery attitude, and he was wildly popular with the Cuban American fans in Miami. But then, unfortunately, in 2016, tragedy struck. Fernandez died in a boating accident off the coast of Miami at the age of 24. This tragedy sent shockwaves throughout his team, his city, and all of baseball. On September 26th, the next day, the Marlins were scheduled to play a game against the New York Mets. And here are some somber scenes from the field that day.
Difficult day in Miami for Marlins fans, even for Met fans, for baseball fans. Marlins Park. This about 3 hours ago, D. Gordon with Jose's glove and Jose Fernandez cap and a baseball. Tonight, the Marlins will play a baseball game. Just 36 hours from learning that they had lost their ace.
I don't know how they're going to do it, but the Miami Marlins are going to play a baseball game against the Mets tonight. I was especially struck by the poignancy of the national anthem, a song we hear every day. But for a young man who risked everything to be a part of this country, it rang especially true today.
But by the time the game was over, it became known as the Marlins Miracle. Here's why. D. Gordon, one of Fernandez's best friends, was the first batter for the Miami Marlins. With over 300 at-bats so far in the season, he had not hit any home runs. Then, at that first at-bat on this day, he did this.
Gordon has started to look like the D. Gordon of last year. Gordon to right. It's deep. And it's gone! D. Gordon has hit it out. And the Marlins have a 1-0 lead.
That special home run and that special moment became known as the Marlins Miracle. It made headlines across the country as the nation was inspired by D. Gordon's heroic hit. But here's the thing. If we look at the situation a bit more carefully, there may be another potential hero in this story, a hero that can only be revealed through a study of statistics. And that potential hero is this guy, Bartolo Colon, the opposing pitcher during D. Gordon's at-bat. So that raises our key question for today. What role did the pitcher play in making the Miami Marlins Miracle? With that question in mind, let's move into our guided notes. We're going to cover 2 topics today, starting with using values to find proportions in normal curves. So let's talk about this pitcher, Bartolo Colon. At the time, he was 43 years old. He was loved by fans, players, basically everyone who interacted with him. And he had an iconic name, which he fully owned and used to refer to himself, the Big Sexy. And there's a reason for that, because at 43 years old, he was still making plays like this.
He's just keeping the ball away from Bohr the whole game. He wants to get it.
There, ball behind the back flip, and he got him! Oh, wow! It's so easy for Colon right now that he's able to put some mustard on it.
And also, impressively, despite his age, Colon still threw very fast. Among first-inning fastballs that he threw in that 2016 season, his average pitch speed was 89.4 miles per hour. To put that speed in context, that means that the hitter, standing 60.5 feet away from the pitcher's mound, only sees the ball for less than half a second of flight time before it reaches them. It turns out that if you look at the distribution of speeds among all of Colon's first-inning fastballs that he threw that season, they are well modeled by a normal curve, the one that you saw in the lesson starter, with a mean of 89.4 miles per hour and with a standard deviation of 1.7 miles per hour. And so, according to the empirical rule, about 68% of his first-inning fastballs were between 87.7 and 91.1 miles per hour, or within 1 standard deviation of the mean. 95% of his fastballs were between 86 and 92.8 miles per hour, or within 2 standard deviations. And then 99.7% of his fastballs were between 84.3 and 94.5 miles per hour, within 3 standard deviations of the mean. So with this distribution, we can look at a question like this. What percent of his fastballs were 92 miles per hour or faster? As with all normal curve problems, to tackle this, we should use these 3 steps. First, draw and label the curve, then perform the calculations, and finally answer in context. So the first step when answering this question is to draw and label the normal curve associated with Colon's fastballs. So we do that here, and note that we've labeled the curve as normal with a mean of 89.4 and standard deviation of 1.7, and we've put labeled tick marks showing those standard deviation markings. So to answer the question, we need to find the proportion of fastballs that were at least 92 miles per hour. Remember that the phrase at least means that 92 is the least speed we're looking for. So we're looking for 92 miles per hour or higher. That is, we're trying to find the percent of his fastballs that are in this upper shaded area, or the probability that this random variable is greater than or equal to 92, which we can write using this notation. Now that we have a good picture of what the question is asking, it's time for calculations. And we can see that 92 is not exactly a convenient number for our curve because it doesn't fall on one of the labeled tick marks. So what do? Well, when you're between standard deviations in your normal curve, it helps to find the z-score. Then use technology to finish up the calculations. So we can see that 92 is more than 1 standard deviation away from the mean, but it's less than 2 standard deviations away. And that means that 92 miles per hour is between 1 and 2 standard deviations above the mean speed of 89.4 miles per hour. To find out exactly how many standard deviations above the mean, we find the z-score. Recall that z-score shows you how many standard deviations a data value is above or below the mean. And recall that the formula for the z-score is the data value minus the mean in the numerator, which shows us the distance between the data value and the mean. And then we scale that difference by putting the standard deviation in the denominator to divide by it. And that lets us figure out how many standard deviations the data value is above or below the mean. Our data value is 92, so we can drop that in. Then the mean and standard deviation come from the probability distribution we've already written, and we substitute them in. and that calculates that the pitch speed of 92 is 2.6 miles per hour above the mean. When we divide this by the standard deviation of 1.7, we get 1.53, which means that 92 miles per hour is 1.53 standard deviations above the mean. And so using that z-score, we can figure out what percent of his pitches will be more than 1.53 standard deviations above the mean. And you can do this using your preferred calculator or software. There are short videos linked in the description that show you how to do this for a number of resources. So check those out before proceeding. So as shown in the video for your preferred calculator or software, we get an area of 6.3%. So 6.3% of his fastballs are at a speed of at least 92 miles per hour. And this should make some sense, because recall that the empirical rule tells us that 95% of data values are within 2 standard deviations of the mean. So only 5% total will be outside of that, or 2.5% in each tail. And since our data value was only 1.53 standard deviations away from the mean, rather than the full 2 standard deviations away, there is slightly more area above it. And 6.3% is slightly higher than 2.5%. And now that we have the proportion, our final step is to answer the question in context. So we can say that 6.3% of his fastballs were at least 92 miles per hour. So this means that at age 43, really pretty uncommon in baseball, Colon was still throwing at least 92 miles per hour 6.3% of the time. That is quite impressive. And now that we've looked at some of his fastest pitches, we can also ask what were some of his slowest fastball speeds. And that brings us to our next topic, using proportions to find values in normal curves. Specifically, we're going to answer this question. What speed is at the 5th percentile of his fastballs? That means we need to find a speed that's only at or above 5% of his pitches. First step, as always, is to draw and label our curve. We're given that the pitch speed we're looking for is above about 5% of his pitches. So we've shaded an area that seems to contain about 5% of the probability below it. And we're trying to find the pitch speed at that spot, which we don't know yet. So we put an X there. Our goal is to find that unknown value. And using our notation, we'd say that the probability that our random variable, capital X, pitch speeds is at or below the unknown value, lowercase x, is 5% or 0.05. So we can ask what z-score leaves just 5% of the curve below it. Again, linked in the description, we have some videos that take you through how to find that z-score using your own choice of calculator or software. So check that out and then return to this video. So using your choice of technology, you found that a z-score of negative 1.64 leaves 5% of the area in the lower tail of a normal curve. In other words, we need to find the pitch speed that is 1.64 standard deviations below the mean. We can go right back to the formula for z-scores. This time, the data value is what we're trying to find. We know the mean and the standard deviation, and we also have the z-score this time. If we plug them in, the data value x is the only remaining unknown. So that's what we solve for. To solve, we need to undo this division of 1.7 by multiplying both sides by 1.7, and that cancels the denominator so that the equation becomes simpler. To undo the remaining subtraction of 89.4, we can add it to both sides and get a value of 86.6. So the pitch speed we're looking for is 86.6 miles per hour. Of course, the last step is to answer the question with context. So we can say that 86.6 miles per hour is at the 5th percentile of Colon's fastball speeds. So this means that an 86.6 mile per hour fastball is unusually slow for him. It's only faster than 5% of his pitches. Now, with this information in mind, let's watch the Marlins Miracle clip again. But this time, pay attention to this part of the screen, which shows the pitch speed measured for his fastball.
Of last year. Gordon to right. It's deep.
So that pitch speed in the clip raises our discussion question for today. Here are the locations of all the pitches Colon threw to D. Gordon in that 2016 season. And note that pitches near the middle of the strike zone, or towards the middle of the box shown here are considered easier to hit. This dot right here shows the Marlins Miracle pitch, and it was only thrown at 85.7 miles per hour. Given the location and slow speed, Cologne was asked in a post-game interview if he purposely threw an easy pitch. Cologne ended the interview early and walked out. So this brings us to our discussion question. Do you think Cologne purposefully threw an easy pitch? Justify your answer using a normal curve calculation. And here's a hint to get you started. Using the normal curve from this lesson, try to find the probability of him throwing a fastball that's as slow as the one he threw to Gordon, 85.7 miles per hour or slower. With that in mind, take a moment to jot down your response to this question for discussion in class. That's it for today, statisticians. We'll see you next time.